We all know AI is getting smarter and smarter, but it's also getting incredibly hungry for memory. So today, we're diving into a breakthrough from Google that pretty much acts like a shrink ray for AI, tackling one of its absolute biggest challenges. It's called TurboQuant, and honestly, the results are just stunning.
So let me just start with this question. What if you could make our AI models not just, a little bit better, but dramatically faster and leaner? And I'm talking up to 8 times faster while using 6 times less memory. It sounds like something out of science fiction, right? Well, the researchers behind TurboQuant actually made it a reality.
All right, so here's our game plan. We're going to start with the core problem, what we're calling the AI memory crunch. Then we'll look at why the old fixes just aren't cutting it before we introduce the hero of our story, TurboQuant. We'll uncover its 2-step secret, look at the mind-blowing results, and then wrap up by asking, what does this all mean for the future of AI?
Okay, first up, the AI memory crunch. You see, as these huge AI models get more and more powerful, they also become unbelievably hungry for memory. And this creates a massive bottleneck that slows everything down and, you guessed it, drives up the costs.
Now, to really get why, we need to talk about something called vectors. An AI model doesn't see words or pictures the way we do. For them, everything is boiled down to these complex mathematical objects, these high-dimensional vectors. Think of them as the rich, super detailed language AI uses to understand the world. They're incredibly powerful, but man, do they take up a ton of space.
So where do all these vectors actually get stored? Well, they go into something called the key value cache, or KV cache for short. The best way to think about it is as the AI's high-speed digital cheat sheet. It uses it to quickly remember stuff from earlier in a conversation without having to reread everything from the start. But as that conversation gets longer, the cheat sheet just gets totally cluttered and slow, and that becomes a huge performance problem.
So the obvious fix seems to be, well, just compress all the data, right? But that leads us to what the researchers call a compression conundrum, where the old fix has a hidden and pretty serious flaw.
So the standard way of doing this is called vector quantization. Its whole job is to shrink those big vectors down to save space. But here's the catch. It introduces this thing called memory overhead. For every chunk of data it compresses, it has to store extra information. It's kind of like trying to pack a suitcase that's already half full before you've even put anything in it. It adds back 1 to 2 extra bits for every single number, which really starts to defeat the whole purpose of compressing in the first place.
And this is where our story gets really good. Enter TurboQuant, Google's incredibly elegant solution that was designed specifically to get rid of this memory overhead problem.
And I just love how the researchers themselves put it. They say this isn't just another compression tool, it's an algorithm that optimally addresses this specific challenge. It was built from the ground up to eliminate that half-full suitcase problem for good.
So how does it pull this off? Let's get into the 2-step secret behind how TurboQuant works its magic. This is where it gets seriously clever.
It's basically a 1-2 punch. First, a method called PolarQuant compresses the data from a completely new, angle. Then a second algorithm called QGL comes in to clean up any tiny errors that are left behind, and it uses this brilliant 1-bit trick.
Okay, let's break down that first step, PolarQuant. It's all about changing your perspective. So instead of using standard coordinates, like telling someone, go 3 blocks east, then 4 blocks north, it converts that to polar coordinates. That's like saying, go 5 blocks at a 37-degree angle. And this gives you 2 things, a radius for strength and an angle for meaning. That simple switch completely eliminates the need for that costly memory overhead. It's gone.
Now for step 2, QJL. It's a bit of a mouthful. It stands for Quantize Johnson-Lindenstrass. After PolarQuant does all the heavy lifting, there's still some tiny residual errors. So QJL acts like a mathematical error checker, a fine-tuning tool that just sweeps in and cleans up those inaccuracies with incredible precision.
And here is the real magic of QJL. It takes all that complex error data and reduces it down to a single sign bit, either a +1 or a -1. That's it. It achieves perfect error correction with literally 0 memory overhead. It's just an incredibly efficient 1-bit trick. So, the theory sounds fantastic, right? But does it actually work in the real world? Let's move on to the impressive results and see how TurboQuant did when they really put it to the test. First up, in those super demanding needle-in-a-haystack tests, where the AI has to find one tiny piece of info in a massive document, TurboQuant slashed the key value memory size by a factor of 6, a 6x reduction for one of the hardest tasks an AI can do.
And what about accuracy? I mean, shrinking is great, but not if it gets dumber. Well, check out this chart. On the long bench benchmark, at just 3.2 bits, TurboQuant keeps 95% of the original model's performance. It's easily beating other methods like just using PolarQuant on its own or the Kiwi baseline. So it's not just smaller, it's smarter.
But it's not just about saving space, it's also about speed. When they tested it on powerful H100 GPUs, TurboQuant delivered up to an 8x performance boost when computing something called attention logits, which is basically the core math an AI uses to figure out which words are most important in a sentence. It's not just shrinking the data, it's making the AI think faster.
And this might be the most stunning number of them all. It can compress that KV cache all the way down to just 3 bits per number. And get this, it does it with zero loss in model accuracy and without any expensive retraining or fine-tuning. That is what I call extreme efficiency.
So what does this all mean? Let's zoom out and look at the future of efficiency and really understand why a breakthrough like this matters for all of us.
The real-world impact here is huge. Think about the speed and quality of semantic search, the kind that powers Google. This makes it faster, more efficient. It directly solves those memory bottlenecks in massive models like Gemini. It lets companies build enormous vector databases without needing mountains of memory. And it does all of this with top-tier accuracy right out of the box. And here's what makes this so trustworthy. TurboQuant isn't just some clever engineering hack. As the researchers make really clear, it's a fundamental algorithmic contribution. It's backed by solid, rigorous mathematical proofs, which means it's robust, it's reliable, and it's ready for critical large-scale systems.
Which really just leaves us with one final big thought. As AI continues to weave itself into every part of our lives, from our search engines to our creative tools, the battle for resources is only going to get more intense. So, could it be that this kind of extreme, mathematically proven efficiency is actually the final frontier in making AI accessible and sustainable for everyone?